On to the next section, which involves inverses of matrices. So section 1.5, inverses of square matrices. So the plan is to define the inverse of a matrix, give a technique to find the inverse. Not all matrices are invertible, so find the inverse when it exists. And all these are going to use elementary row operations. So the agenda here is going to be actually quite similar to what we did in the previous section in terms of row reduction with a certain plan. The plan is very slightly different in this section. We'll deal with an augmented matrix. It's a little more, it's bigger in this section. So there's more arithmetic involved. But in a sense, this is fairly redundant with what we did when it comes time to actually find inverses with what we did in the previous section with systems of equations. The formal definition, an n by n matrix A is said to be invertible if there exists an n by n matrix C such that A times C equals C times A equals the identity. If A is not invertible, then it's called singular. Think of the word singular, you know, just between you and me, think of the word singular as bad. This word pops up in math again and again, and in bad settings. Non-invertible matrices are bad. Singularities come up in differential equations where there's a division by zero. The center of a black hole is called a singularity because not so much of matrix ideas, but because of that word coming out of differential equations. But when you hear singular, kind of think informally, it's bad. We're looking for inverses of matrices when they exist. We'll have a technique that'll tell us, here's the inverse if it exists, and that technique will fail, of course, if the matrix isn't invertible. So we'll be able to tell whether we've got an invertible matrix or a singular matrix, and when invertible, we'll be able to find the inverse. Similar to the situation with systems of equations. We'll use a Gauss-Jordan type method, and we'll get the answer unambiguously. All right, we'll see examples of matrices that don't have inverses. In fact, we'll give a bunch of conditions that are equivalent to the invertibility of a matrix. And when the inverse exists, it's unique. So let's take care of this kind of technicality, and we'll get down to actually computing these in another couple of slides, a couple pages. Theorem 1.9, uniqueness of an inverse matrix, says an invertible matrix has a unique inverse. So we'll use this notation. A inverse is the way to read this, capital A being a matrix. They say this is an invertible matrix. So there's the assumption of an inverse existing. When an inverse exists, it's unique, is an alternate way of saying this. Okay, common math way to prove things. I like the looks of this because it's only 3 lines. Common way to show uniqueness in math is to suppose you've got two of these things. Suppose C and D are both inverses of matrix A. We want to show C and D are actually the same. So there's not two different inverses. All right, consider D times A times C. Well, since D is an inverse of A, then D times A would be the identity. That's what inverses are. The identity times C would be C itself. Implicit in all this is these are all square matrices, say n by n matrices. We only defined inverses for square matrices. Now let's consider D times AC. Same thing by associativity. Well, we've assumed C is an inverse of A as well. So A times C is the identity, and the bracketed together quantity must be the identity, so we get D times the identity is D itself. Well, dA times C equals D times AC, associativity. So this quantity we just saw equals C, this quantity equals D, C equals D, there's the uniqueness. Okay, so when they exist, inverses are unique. Unfortunately, inverses don't always exist for square matrices. We'll have loads of condition on the invertibility of a matrix. If we wanted to invert elementary matrices, remember elementary matrices from last section, matrix is an elementary matrix if it results from taking an appropriately sized identity matrix and applying one elementary row operation to it. We have three elementary row operations: row addition, multiplication of a row by a scalar, scaling rows, I think they call it, and interchanging rows. So those are the three elementary row operations. Each has a corresponding elementary matrix for any particular elementary row operation. Suppose elementary matrix E1 interchanges row 1 and row 2 of a 3x3 matrix. So we'll go to the supplements and see how to invert that. How do you think you undo interchanging row 1 and row 2? So you're going to swap row 1 and row 2. How do you undo that? Swap them again, swap them back. So I bet you that's its own inverse. Let's look at that more specifically in the supplemental notes. Okay, E1 interchanges row 1 and row 2 of a 3x3 matrix. All right, so we'll take the 3x3 identity matrix and interchange row 1 and row 2 in it. And that'll produce this elementary matrix E1. That gives us a second elementary matrix. E2 multiplies row 2 by 7 in a 3x3 matrix. Okay, so we'll start with the 3x3 identity, multiply row 2 by 7, introduces a 7 here. Of course, with elementary matrices, we could perform this row interchange on a 3x3 matrix A by multiplying A on the left by this elementary matrix. And similarly, we could multiply row 2 by 7 for 3x3 matrix A by multiplying A on the left by this elementary matrix. All right, well, how would you undo this? How do you undo swapping row 1 and row 2? Swap them back, interchange them again. How would you undo multiplying row 2 by 7? Divide row 2 by 7. All right, so we get E1 inverse would be, it's actually E1 itself. How do you swap these back? Just swap them again. And indeed, if you'll take this matrix and multiply it by E1, or take this matrix and multiply it by itself, you'll get the identity matrix back out. That's what inverse matrices are. How do you undo multiplying the second row by 7? Divide the second row by 7. You take this matrix and this matrix, take a product of them, and maybe this one's even easier to see, you're going to get the identity matrix. Yeah, first row, third row, first row, third row, first row, third column as well. These look like identity matrices. It's the second row or the second column is the only one that's different from an identity matrix. And if we were to multiply these two together, we'd get, regardless which one comes first, we'd get, for say the second row, 0, 7 times 1/7, 0. And so we're good to go on a 0, 1, 0 in the product. Indeed, this checks by multiplying that these are actually the inverses. So total piece of cake just to look at an elementary matrix and see how to undo it, how to find its inverse matrix, I should say. We didn't illustrate adding one row to another, but hey, how would you undo adding twice row 1 to row 2? By subtracting twice row 1 from row 2. So it would be a similar type manipulation of the corresponding elementary matrices. Okay. We've dealt with some properties of products before, matrix products, behave in kind of oddball ways. This is going to remind you probably of a transposition property we had a section or two ago. Let A and B be both n by n matrices, invertible. Okay, so A inverse and B inverse exist and are unique by theorem 9. then A times B is also invertible, and the inverse of A times B is B inverse A inverse. Order matters, and somehow in the manipulations, these got turned around. We had A before B, then we took an inverse, and now we get the B before the A, and the B inverse before the A inverse. Well, let's check it out. How are you going to make sure this B inverse A inverse really is the inverse of AB? Let's multiply this times AB and see if we get the identity out. That's what an inverse is by definition. Okay, so let's take AB times B inverse A inverse. We've got associativity going on, so we'll regroup things here. So let's group the B and the B inverse together first. So we'll group them like that. Hey, B times B inverse, that's the identity. That's what an inverse is. All matrices are n by n in this conversation. Hey, matrix A times the identity matrix, that's just matrix A. And now we've got A times A inverse, and indeed, that's just that's the identity matrix. So yeah, A times B times B inverse times A inverse gives the identity. We've got a good candidate for an inverse. At this stage, we need to check the opposite order. We've taken AB times B inverse A inverse. We also need to confirm, if we'll look back at the definition, that B inverse times A inverse times AB, swap the orders on these two, that you also get the identity. Of course you do. It's similar. You'll associate the A and the A inverse first, get an identity in the middle, then B and B inverse will multiply to get the identity. So it's quite similar to this. And we get both of these satisfied. AB, B inverse A inverse equals the identity. B inverse A inverse times AB equals the identity. AB is invertible, and its inverse is B inverse A inverse. Okay, so we can find symbolically at least inverses of products. All right, I'm going to relate this now to systems of equations. Lemma 1.1, condition for AX equals B to be solvable for all vectors B. Of course, you're thinking system of equations. A is a coefficient matrix. X is the vector of unknowns, and vector B is the right-hand sides of that system of equations. Now, in our conversation here, we're going to indirectly at this stage relate this to inverse matrices, which means we're going to have square matrices in the appropriate places. Coefficient matrix A will be hypothesized to be a square matrix. You only talk about inverses for square matrices. All right, let A be an n by n matrix, so it's square. Claim is the linear system AX equals B has a solution for every choice of vector B, if and only if A is row equivalent to the n by n identity matrix I. All right. First off, you know how to check and see if A is row equivalent to the n by n identity matrix? Yeah, that's what we did in the last section. You do that Gauss-Jordan type stuff to it, looking for pivots down and to the right, down and to the right, down and to the right, and you want those pivots to be 1. You want zeros below the pivots, zeros above the pivots. You take that matrix A, if you can put it in reduced row echelon form, and nothing goes wrong, in a sense, if every column has a pivot, you'll get the n by n identity matrix out. By the way, you would find a unique solution to the system of equations as well. I won't go through proof of this because that's sort of the thing we do. But if you'll think how you would solve this system of equations, you'd go through, we're looking for a solution every time. All right. You'd be looking for a value of x sub 1, x sub 2, and so forth. That's going to work if A is row equivalent to the n by n identity matrix. And you'll be able just to read off the values of x1, x2 after you've done the reduction in the corresponding system of equations. So the reality of this, the correctness of this, that shouldn't be a surprise. Let's go through the proof nonetheless. Okay, so it's an if and only if results. We have to go in a couple of different directions. First, suppose A is row equivalent to the identity. Let B be any column vector in Rn. We're trying to show Ax equals B has a solution for any column vector B in Rn, or every column vector B in Rn. Okay, we'll consider A augmented with B. You know, we've assumed that A is row equivalent to the identity, so we could take this system of equations, reduce it down. We often wrote H augmented with C in the previous section. Here, I know what matrix we're going to get when we do the row reduction. We're going to get the identity matrix. That's the hypothesis. And then something happens to the B vector as we do those manipulations. Well, do you have a solution for the system of equations associated with this augmented matrix? Yeah. First unknown equals first component of C. Second unknown equals second component of C. Last unknown equals last component of C. X1 equals C1, X2 equals C2. It's likely the symbols we would use. So yeah, this has a solution. In fact, it has a unique solution. I can tell you what it is. It's X vector equals a C vector. Here we go. X vector equals a C vector. Theorem 1.6 tells you the solution to this system of equations is the same as the solution to the original system of equations because of the row equivalence stuff. You got X equals C as a solution here. It's also a solution to this system of equations. Regardless of what vector B was, we get a solution. In fact, we get a unique solution out of this. Uniqueness wasn't really mentioned up here. It's hidden in some of the logic, but they didn't say anything explicitly about unique solutions. So row equivalent to the identity implies solutions exist for all vectors B. Unique solutions. Okay, let's look at it from the other logical direction. Suppose A is not row equivalent to the identity. All right, what we're going to do is show A is not row equivalent, so that's not, so we're looking at the contrapositive of the statement. If A is not row equivalent to the identity, we need to show the negation of this. The linear system AX equals B does not have a solution for every choice of column vector B. All right, so what we're going to do is find a specific vector B for which this system has no solution. So that's the plan. All right, suppose A is not row equivalent to the identity. Well, row reduce A to a reduced row echelon form, call it H. H can't be the identity because A is not row equivalent to the identity. So something goes wrong. What's going to go wrong? The last row, so the nth row of this matrix here must be all zeros. Somewhere in there, there must be a row of all zeros. There's a pivot-free column as a consequence. Being in a reduced row echelon form means you put that row of zeros at the bottom. So I know that last row of matrix H must be all zeros. All right, we're going to use that idea to get a contradiction in an associated system of equations. We're going to get 0 equals not 0 somehow or other. We just got to find the right vector to put in for vector B in the system of equations AX equals B. So here's where we are. A is not row equivalent to the identity. All right, well, reduce it down to a matrix H that's in reduced row echelon form. That's got to have a row of zeros at the bottom. All right, how did you get A reduced to H? By a sequence of elementary row operations. Each of those elementary row operations, theorem 1.8, can be represented by an elementary matrix. So we did a first elementary row operation to matrix A, a second elementary row operation to matrix A after the first row operation, and so forth. Say we did T of them. So we did T elementary row operations to take matrix A and turn it into matrix H. And yeah, equal sign's right, not the tilde, not the row equivalent thing. This collection of row operations changes matrix A into matrix H. Okay, we know each of those elementary matrices are invertible. We illustrated it really by example. It's easy to invert elementary matrices. So what we're going to do is take the nth standard basis vector for Rn. Take it as a column vector. What's the nth standard basis element of Rn? It'd be 0, 0, 0, 0, 0, 0, 1. So the last component is 1, and all the earlier components are 0. The last component is 1. Remember how up here we had the last row is all zeros? So we're going to get these zeros together with that 1 somehow. Okay, so take E sub n, the nth standard basis vector for Rn, as a column vector. Define vector B to be E sub t minus 1 up through E sub 1 inverse times that vector E sub n. This vector B is going to be a bad vector. That system of equations won't have a solution when we choose this as vector B. We're trying to show this system of equations doesn't have a solution for all B. That is, there exists some B for which no solution. We're going to show this is such a choice of B. It's symbolic because we don't have any numbers. Okay, so let's take then the system of equations, AX equals B, and watch something go wrong. Okay, it's got augmented matrix, A augmented with B. What we're going to do is apply these elementary matrices, or if you like, the corresponding elementary row operations, to the augmented matrix. That's going to reduce A augmented with B to something else. What's going to happen to A? Well, I can express it in terms of these elementary matrices. We're going to get E1 times A, E2 times that, E3 times that, up through this final elementary matrix. And we'll do the same thing to vector B. What was vector B defined as again? For some reason, we took vector B to be E sub t minus 1 through E sub 1 inverse times that standard basis vector. Why do we do that? Well, here's why we did that in hindsight. So we're going to do the same thing to matrix A that we do to vector B. First rows added together or whatever. Same elementary row operations are done to the rows, so we can perform on vector B, those with elementary matrices as well, thinking of B as an n by 1 matrix. But we've defined B to be the inverse of these elementary row operations applied to E sub n. So when you multiply these two matrices together, it's a matrix and its inverse. It gives you the identity, and you're just left with the E sub n. What happens to matrix A when you do this stuff to it? Well, that turned it into that matrix H. That's where these elementary matrices came from, in fact. And what was up with matrix H? Its last row was all zeros. What's up with E sub n? Its last entry, or its last component, is 1. And all the other components are 0. But what you get in the last row of the system of equations associated with this augmented matrix is 0 equals 1. All right, last row of H consists of all zeros left of the partition and a 1, the one that this vector contributes to the right of the partition. Hey, you can't have 0 equals 1. Isaacs theorem 1.7 part 1 that said there's no solutions. You don't remember all them theorem numbers, I suspect. I'm pretty spotty on them, and I've been doing this for years out of the same book. Yeah, they'll think about it. 0 equals 1 is a problem. And that's what you get correspondingly in the system of equations with this augmented matrix. So no solutions. So this vector B that we introduced at the bottom of the previous slide, AX equals B, no solution. So not all B in Rn have a solution if matrix A is not row equivalent to the n by n identity matrix. It was a if and only if result. We've shown if this applies, then that applies, and we've shown, strictly speaking, if this doesn't apply, then that doesn't apply. It's the contrapositive of the converse, if you like, logic. And who doesn't? Let's get back to the notes. See if we can't make some use out of this. So what was up really with a punchline here? We got a solution if and only if A is row equivalent to the n by n identity matrix. Let's look at an example. Back to here. It illustrates a use of that. Question is, an oddball question maybe at this stage, but you're going to see this kind of thing again and again. Ooh, there's the word span. Oh, it's been a while. When we were talking spans of sets of vectors 2 or 3 sections ago, was a what the hell was it? The set of all linear combinations of those vectors, I think it was. It says determine whether the span of the column vectors of matrix A is the span of R4. So do these 4 columns span R4 is the question. Okay. Gee, how could we get a linear combination of the columns of matrix A? This is how. Remember note 1.3.A? I made a big deal out of it. If we look at A, matrix A is given here, times vector X, where X is an R4. Here, should read X as an element of R4. AX then is a linear combination of the columns of that matrix. So what we're really asking is there a vector X such that A times X equals B? We need to be able to see if this can be done for every B in R4. We're trying to show that the linear combination of these columns can produce any vector in R4. That is, linear combinations of these 4 vectors span R4. You give me an arbitrary vector in R4, okay, vector B. We need to see if there's an X vector of coefficients in a linear combination such that AX equals B. Note 1.3.A is what makes the whole thing tick. By looking at AX, you're looking at linear combinations of the columns of matrix A. Okay, so what we need to do is translate this into something we know how to do. We need to see if AX equals B has a solution for every vector B in R4. That's exactly what the last theorem dealt with. So we need to see if matrix A is row equivalent to the identity matrix. If it is, then yes. If it isn't, then no, to answer their question. Well, that's totally what we've been doing in the past, well, at least in the last section. Let's take this matrix and row reduce it. All right, groovy. Let's use this 1 to eliminate that -3 and eliminate that -1 with the usual type of row operations. In the videos, we're going to accelerate that a little bit more at this stage. Take your time. You got access to these notes. You can pause the video. We'll do those row operations. We'll simplify things, something I've drug out at some length in the past, but give me a little break. These have been double checked and triple checked. It's easy enough to make a mistake. I typeset all this stuff, but these have been checked numbers of times. So do these row operations. Indeed, you get the zeros where you wanted them. I mean, of course you do, by the arithmetic you chose. And yeah, we got the first column the way we want it. We have an agenda here. Yeah, we're trying to make this look like the identity. And if you'll think back, when we talked row echelon form and reduced row echelon form, I really wanted to say, make it look like the n by n identity. Yeah, well, back there, it might not have been a square matrix, so that was a problem. But still, we kind of had a motivation to think, geez, if I could get the identity here, I could easily read off the values x1 through x sub 4, say. We're not exactly doing that here. We're doing something a touch more theoretical, but the manipulations are the same. Hey, what do you want to do here? And maybe I could use this -1 to eliminate that -2. I could use this -1 to eliminate that 1. I could change this to a +1 and then do that. I could swap these two to get a 1 there. Let's see what we like. Let's see, did we just rewrite it? Yeah, just rewrote it. Okay, let's use the -1 to eliminate the -2 and the -1 to eliminate the 1. So we'll subtract twice row 2 from row 1. Row 1 minus 2 times row 2, -2 minus 2 times -1, -2 plus 2. Yeah, that'll do it. And just add to row 3, add row 2, gets us zeros there. In the second column, I'm going to need a 1 there before it's over with. So we'll have to come through and multiply the second row by -1. Could perfectly well do it now. Either that, or how about we, since this is the way it's typeset, use this 5 to eliminate this -5, this 5. Excellent. And I'll get some fractions. And I don't see a way to avoid this. We'll use this 5 to eliminate this 3. Okay, we'll have to do some 3/5 stuff. So we're going to get fractions. It looks like we're stuck with fractions in the end. Yeah, we're putting this in reduced row echelon form. If it's got fractions in it, there was no avoiding them. Well, at least we kind of put them off near the end. Okay, so we use the 5 here to eliminate the -5. We'll add row 3 to row 1. Add row 3 to row 1. We'll subtract these two. It's a row of zeros, which is information that allows us really to answer the question at this stage. We're seeing if this is row equivalent to the identity. Well, it can't be. It's going to have a row of zeros in it. So it can't be row equivalent to the identity. I want to take it all the way down to reduced row echelon form. But I can actually answer the question once I see that row of zeros. No, not row equivalent to the identity. So I'll take the 5 and eliminate the 5 here. We'll take the 5 and eliminate the 3. How's that going to work? We'll subtract 3/5 row 3 from row 2. That'll do it. -3/5 times 5 is -3. That gets you the 0 here. So that's the manipulation to be done. Looks like some stuff happens over there in that fourth column, but it produces this. We're going for reduced row echelon form. Like I said, we'll have to make that a 1. We'll have to make this a 1 as well. We'll have to divide by 5 here. Here comes more fractions. But that'll give us, now the first column is in good shape, second column is in good shape, third column is in good shape, the fourth column is not in good shape at all, and there's nothing we can do about it. This is the unique reduced row echelon form for that matrix A, and what's relevant to the question here, that ain't the identity. Well, if it ain't the identity, then no, those columns do not span R4. I can't write any vector in R4 as a linear combination of those column vectors. Lemma 1.1 tells us that. Let's see, back to the notes. Okay, we haven't computed inverses yet. Let's go through one more little technical result. This says if A and C are n by n matrices and C times A, so this is important that they're square matrices, C times A equals the n by n identity, then, and only then, if and only if result, A times C equals the identity. So you know you can't always reverse the orders on multiplying matrices. It's not a commutative operation. Matrix multiplication, not commutative. You can't reverse the orders. You can't say C times A equals A times C in general. Sometimes you can reverse the order. When? Well, if one of the matrices is the identity, of course the identity times A equals A times the identity when the dimensions are appropriate. It looks like here, when we've got C times A equals the identity, then we must have as well A times C equals the identity. We'll go through the proof, not complicated and mostly computational. Hey, what do you think this matrix C is? Must be the inverse of matrix A. Otherwise, we wouldn't have these two types of behaviors. So let's look at a proof of that. Okay, so C times A equals the identity if and only if A times C equals the identity. Okay, here's plan. First, we'll suppose A times C equals the identity and show C times A equals the identity. Let's go ahead and blink ahead, and here's the conclusion. And then we can, well, here's the rest of it. We can just interchange the roles of A and C to get the implication, if and only if, in the other direction. Well, suppose A times C equals the identity. Then, if we look at the equation, system of equations, AX equals B, this has a solution for every column vector B in Rn. Why is that? Because A is row equivalent to the identity. We found a matrix C such that, so we multiplied on the right, but it still involves some manipulations. Yeah, let's do it in terms of substitution. I was heading in the wrong direction there. Let's take X equals to C times B. We'll show that is a solution to AX equals B. There we go. There's something going on here with row operations, or maybe it's column operations, but this is cleaner. Take X to equal C times vector B. And let's plug that in and see if we get B out. It looks like we do. So we'll take AX, that is A times CB, associativity. Hey, A times C, there's my hypotheses. That's the identity. The identity times B is vector B itself. So if we plug in for X, C times B, we get B out. Okay, so indeed, any vector B can be put on the right-hand side of the system of equations, and that system of equations has a solution. We know, here comes the row equivalent to the identity stuff, by lemma 1.1, that happens when and only when matrix A is row equivalent to the identity. So matrix A is row equivalent to the identity. There's a sequence of elementary row operations that we can do to matrix A to produce the identity. Well, we can represent those with elementary matrices. That is, A times E1 on the left times E2 on the left up through E sub T on the left will produce the identity matrix. All right, so we've got then this matrix times matrix A equals the identity, and we've got A times C equals the identity. So here we've got an inverse of A. Here we've got an inverse of A. Theorem 1.9 tells us inverses are unique, so it must be that we get this equals matrix C. And in fact, these are the inverse of matrix A. So we get if AC equals the identity, then CA equals the identity. This is very specific to these being square matrices. I could have non-square matrices of the appropriate dimensions, and we could get C times A equals an identity of one dimension, and A times C equals an identity of a different dimension. So you wouldn't get, I couldn't draw the conclusion necessarily that we get both of these. We're talking different identities. This is only valid when we deal with square matrices. So it allows us to streamline claims about inverses. Okay, here's the big computational thing. So the bulk of the mechanical problems we do will be, here's a matrix, find its inverse, and here's how you do it. Okay, suppose matrix A has entries A sub ij. Finding the inverse, let's let the inverse have entries X sub ij for a second. Then what we want is matrix A times matrix A inverse with those entries to give us the identity matrix. All right, well, this looks similar to some stuff we did with systems of equations, except there's too much stuff over here. We had just a single column vector. Well, treat it then as a whole bunch of systems of equations. Here we've got a coefficient matrix, matrix A, and here we've got, well, let me highlight just the columns. Here we've got a column vector, and we want that matrix times that vector to be the first column of matrix I. Similarly, we got a second column. We want that matrix times the second column to give us the second column of the identity matrix, and so forth. What you really got then is AX equals B style, but we're doing that first for X, these unknowns, and for B, the first column of the identity matrix. Secondly, for X, these unknowns, and then the second column of the identity. So what we could do is write out, how many of them are there? N systems of equations with this is the unknowns, and then this is the unknowns, and this, and this, and this is the unknowns, with the first column here is the right-hand side of the equations, the second column here is the right-hand side of the equations, and so forth. Or we could just paste them all together, and whereas we had A augmented with matrix B, let's just take A augmented with all the columns of the identity matrix. So we're going to take A augmented with the identity matrix, and then what we're going to do is apply the Gauss-Jordan method to take matrix A, reduce it down to the identity. As you do that, what you'll be doing is solving systems of equations that will guarantee that what happens on the right-hand side, what happens to the identity matrix, produces A inverse. So here's how you find the inverse of a matrix. Oh, it's the same stuff we've been doing. You take the matrix, you augment it with the identity matrix of the same size, have to be square matrices. Don't talk about inverses unless we've got square matrices. And do row reduction. If you get down to the identity, you found the inverse. It's what happened on the right-hand side. What if you can't get down to the identity? I bet you it ain't invertible. You can't get down to the identity, this matrix A is not row equivalent to the identity, and this matrix A is not invertible. So just like solving systems of equations, this always works. Here's your n by n matrix. Tell me about its inverse. Well, do this. If you find its inverse, good for you. If you can't find its inverse, if you did this method correctly, it's because it ain't got an inverse. Something went wrong. Something went wrong involving reducing A down to the identity. That's where things would go wrong. A is not row equivalent to the identity. All right, let's actually find an inverse and use it to solve a system of equations. Maybe we'll take a little break in this section. Okay, page 84, here we go. Consider matrix A, 6, 7, 8, 9, find its inverse, and use A inverse to solve this system of equations. 6x1 plus 7x2 equals 4, 8x1 plus 9x2 equals 6. Hey, look, the coefficient matrix for this system of equations is matrix A. All right, so we'll take advantage of that to solve the system of equations. This is a pretty fundamental example. Also, our first computation of an inverse matrix, other than elementary matrices. Okay, form A augmented with the identity. And apply Gauss-Jordan elimination to produce the identity augmented with A inverse if it works. If it doesn't work, you'll know that matrix A is not invertible. At this stage, this is probably the best way we have of determining if a matrix is invertible, is by just trying to find its inverse. We'll have some other techniques before we're done. We'll have lots of techniques. This one's still a pretty easy one. Okay, so take the 6, 7, 8, 9. Geez, these numbers are a little awkward. I need to use the 6 to eliminate the 8. How about we divide that first row by 6? Introduces some fractions, but I get a 1 there. Then I can use the 1 to easily eliminate the 8. Cool, and we get a 0 there. But that 7 6 and 1 6, those guys are going to come along for the ride and give me some fractions. Finding inverses of matrices, fractions are a pretty common thing. I give you a test, they can be avoided with sufficient effort, but we'll be dealing with fractions before things are over with in this class for sure, in systems of equations. And with inverse matrices, we'll probably be dealing with fractions. Maybe we can isolate those fractions at least, and we'll have a plan for that as we go along. Okay, so we got, we use the 1 to eliminate the 8. First column's good. How about we multiply through by -3? on that second row. That'll get us a 1 there. Also got rid of the fractions. And now let's use that 1 to eliminate that 7, 6. So we'll take row 1 and subtract 7, 6, row 2. Take row 1 and subtract 7, 6, row 2. That'll give us the 0 we were looking for there. There's a lot of arithmetic going on the right-hand side. I won't bore you in the video with this. I did show all the arithmetic here. Maybe we'll always do that. Not a bad idea when you got these fractions in there, though. And so it must be that A inverse equals this. You know, we could factor a 1/2 scalar from each of these, bring it out front as a scalar, and eliminate fractions here. And I'd still have a fractional scalar out front, but I could isolate it. Anyhow, there's the inverse matrix. You could multiply that by the original matrix A and see, indeed, you get the 2 by 2 identity matrix. All right, so they wanted us to consider a system of equations. That system of equations had matrix A as its coefficient matrix. There were 2 unknowns, x1 and x2. And I can't squeeze all this stuff on the slides, but the right-hand sides of the equations were 4 and 6, respectively. Okay, well, we've got AX equals B. Now, if these were just numbers, if we had number A times number X unknown equals number B, you just divide both sides by A, and you'd say X equals B divided by A. There is no division for matrices. There's inverses sometimes, but there's no division with matrices. There's only multiplication by inverses. Division really isn't even a math operation. There's multiplication by inverses. Some folks may call it division. There's a button on the calculator labeled division, but that's really just not a legitimate operation. Subtraction isn't legitimate either. There's addition of negatives. Take more advanced math classes and they'll elaborate on that. Your next algebra class, if you take more algebra, is probably Introduction to Modern Algebra, and they'll elaborate on binary operations in more abstract settings. Well, anyhow, I can't divide by matrix A because that doesn't make any sense, but I can multiply by its inverse. Next best thing, actually same thing because division is bogus. We'll multiply both sides by A inverse. And hey, A inverse times A, that's the identity matrix. The identity matrix times vector X is just vector X. And on the right-hand side, we got A inverse B. So if I know the inverse, then I can solve this system of equations. It's X equals A inverse B. If the matrix A is invertible and I know the inverse, this is a whole bunch quicker. Well, that's exactly the information we have. So we must have vector X with components X1 and X2 equals A inverse B. Here's A inverse from the previous slide. Vector B, the 4 and the 6. We'll do the multiplication. It looks like it gives out 3, -2. X1 equals 3. X2 equals -2. There's a solution to the system of equations. And we solved that system of equations without any row reduction, didn't we? Yeah, well, not really. We just hid it upstairs when we found A inverse. But we didn't have to redo it because we had already done it in a sense. We had already done the row reduction involving matrix A. That's where matrix A inverse came from. And that's how we were able not to repeat it here. Okay. All right, let's take a little break. We'll come back and do the last couple of pages in another video and finish up this inverse matrix thing. We'll see you there shortly, I suppose.